Hello everyone, and welcome to our video on the special right triangles. So we have two special right triangles. The first one is a 45, 45, 90, so these are degrees, right triangle. And so it comes from a square with sides that are all 1. And if we cut this square in half diagonally, we could do Pythagorean's theorem to get this hypotenuse, which would be square root of 2. And then we know if we cut a square diagonally that our angles would be 45 and 45. Okay, so let's take that by itself. Okay, so there's our 45, there's another 45, and then here's the right angle. Well, what we do with that special right triangle based on that square is we use similar triangle properties and we just multiply it by something. I usually use n. So if we multiply all of these by the same number, it would be to scale with a similar triangle. So what we're going to write is n, and n square root of 2. Okay, so this is going to be true for all right 45, 45, 90 degree right triangles. So we'll show how we use this in just a second with some different cases. Let's get our other special right triangle. The other special right triangle is the 30 degree, 60 degree, 90 degree right triangle. And it comes from using a equilateral triangle. So those were all 1. We know an equilateral triangle has all 60 degrees. But if we cut it down half, actually instead of 1, sorry, let's change it to 2. That makes it easier. There we go. They're all 2. So if we cut that in half, that makes this length 1. And then we can use Pythagorean's theorem again to get the height of this right triangle, which would be square root of 3. Okay, so let's draw that bigger, just that piece. Okay, so and this is not to scale, so my drawing's a little off, but let's say that this is 60. If this is 60 on the left, and I know it's a right triangle, so we cut it down right in half, right triangle, we would know that that's 30, so that needs to add up to 180. And then just like before, so if we multiply all of those by the same thing, so if I multiply that by n, that by n, and that by n, we get a right triangle 30, 60, 90 that has the same similar properties as any 30, 60, 90 triangle. Okay, so notice the 30 degree angle, so that's my focus, starts with n directly opposite. The hypotenuse is to double it, and then the medium side is to multiply by radical 3. Okay, so we set this up just like this. Okay, and there's two things that we do with them. We could either evaluate trig functions, or we could start to use them to solve different triangles. So we'll show those both here. Okay, so if we evaluate these trig functions using this right triangle, so I have the 30, 60, 90. Again, I'm just going to draw it. It's not to scale. Okay, so directly across of 30 is the n. The other leg is n radical 3, and the hypotenuse is 2 times n. So if I do the sine of 30, let's mark those up. If I'm doing SOHCAHTOA, that means, so 30 is the angle I'm focused on. Opposite of 30 is over there. Here's the adjacent of 30. And then 2n, no matter what's the hypotenuse. Okay, so remember SOHCAHTOA is using, for sine of 30, the opposite over the hypotenuse. And so our opposite side is n. Our hypotenuse is 2n. Notice the n's would just cancel, and it's 1/2. Okay, so this right triangle is a way to help us evaluate trig functions if we really wanted to, instead of using the unit circle. So the unit circle could have also been used on this problem. So there's the 30 degrees, or if we had it in radians, pi6 as the angle, sine is the y coordinate. Okay, so it gives you the same answer. Okay, but just to use, so cosine of 45 you might already know based on the unit circle. Okay, so real quick, there's my very quick sketch. However, let's use the right triangle just to show it. Okay, so I've got, here's 45, 45, 90. Each leg is n, and then the hypotenuse is n radical 2. Okay, so the 45, 45, 90, again, this, I'm going to say this is the 45 angle I'm focused on, which makes that the opposite, this the adjacent, and then regardless, this is the hypotenuse. Okay, so cosine using SOHCAHTOA is the adjacent over hypotenuse, which means on this problem, my adjacent is in, my hypotenuse is in radical 2. Again, the ints cancel. We have 1 over radical 2. And then we could rationalize this to get radical 2 over 2. Okay, which is the same thing we would have gotten if we used the unit circle. Okay, so they're always going to agree. So this is just a different way to show it. Okay, so that's using them to evaluate some trig functions. We could also have done it with tangents or cotangents or so forth. All right, let's see how we can use them in just right triangle problems. Okay, so we're going to use these special right triangles. You could use SOHCAHTOA, but because of the special angles, we're going to use the special right triangles instead. All right, so in this example, it says find x in the isosceles. So isosceles means that two sides have to be the same. And in this case, it would be those two sides because the hypotenuse is always the longest. So the hypotenuse can't be equal to another side. Okay, so it says isosceles right triangle. So that means this must be 18. If these two sides, 18 feet, there we go. If those two sides are the same, then their angles opposite to them also must be the same. The only way for those to be the same would be for them to each be 45. Okay, so this is a 45, 45, 90 triangle. So I'm going to mark these. This would be in, this would be in, this would be in radical 2. Well, in either of these cases, I'm just going to focus, let me try that again. I'm just going to focus on that top one and say, well, this information right here is telling me that n is 18. So if n is 18, how about I just change that n right there to 18? So we get x is equal to 18 radical 2 and then feet. Boom, that's it. Okay, so instead of doing Pythagorean's theorem, 18 squared plus 18 squared equals the hypotenuse squared, we did it much faster. So if you want to double check, this will show, so hypotenuse is x. This will eventually show that's the same. Okay, so that's real nice. So it's just kind of setting up your special ratios and within and continuing to solve. All right, this other one. Okay, so that's my only special right triangle. So if we had a 30, 60, 90, so I'm skipping the 30, 60, 90, it looks like, we could, I probably have one later. Okay, we could set it up in a similar fashion. So all it is still just setting up your in radical 3 and 2. And so I think we're going to see that in a different video. That's it. All right, so thank you for watching. If you do have any other questions, please let me know, and I'll see you again soon.